Today we'll learn about inverses of functions. There are really two ways that we can find inverses. The first is algebraically, and the other is graphically, neither of which should really be too much of a surprise. So we're going to do this with examples. Our first example is to find the inverse of the function f of x equals 2x plus 3. So the first thing you need to do, if you want to think about these in steps, is to replace your f of x with y, just to make your math easier as we go. So I'm going to rewrite this f of x and call it y for a minute. So I have y equals 2x plus 3. For our second step, we switch x and y. And switching x and y is really the key step to finding an inverse. So where I see a y, I call it x, and where I see an x, I call it y. So now I have x equals 2y plus 3. And then we solve for y. So get your new y alone. So here we'll subtract 3 from both sides and divide by 2. So y is x minus 3 over 2, or 1/2 x minus 3/2. Either way is fine. We'll leave it like this for now. And then finally, you use inverse notation. Inverse notation, to show the inverse of function f, we write it as f to the negative 1 of x. That does not mean a reciprocal. It's not a negative exponent in terms of exponent rules. This entire expression, f to the negative 1 of x, means inverse. So oftentimes you'll see a problem that says find f negative 1 of x, and you need to think of that as the inverse of x. That's what they're looking for, and that's when you go through this process. So finally I replace y with inverse notation, f negative 1x, and so I can say the inverse of f of x, which was 2x plus 3, is x minus 3 over 2. And that is how it works. So let's just practice a couple. For exercise 2, we want to find the inverse of g of x equals 2x cubed plus 1. So again, we'll replace g of x with y, when we have y equals 2x cubed plus 1. We'll switch x and y, that critical step of finding an inverse. So x equals 2y cubed plus 1. And then we need to get y alone. First I'll subtract 1. I'll divide through by 2. And I need to undo this cubing. Well, to undo cubing, you cube root. You can think of that again with our new exponent rules as raising this 3 to the 1/3, which means cubed root. What we do to one side, we do to the other. We will prefer, for graphing reasons, to write this as a root. So this is the cubed root of x minus 1 over 2. And then finally you use your good inverse notation. So this function's named g, so we'll say the inverse of g of x is the cubed root of x minus 1 over 2. And you're done. So it's a pretty quick and simple process. Replace your f of x notation with y, switch x and y, solve for y. We can also find inverses graphically, but something you need to understand is that only one-to-one functions have inverses. So let's review what that means. A function, of course, passes the vertical line test. So a one-to-one function passes the horizontal line test. In other words, the y values never repeat. So a one-to-one function, the y values never repeat, and it passes the horizontal line test. So if you have the graph of a line, any old line, you're fine. It passes the horizontal line test. Where you'll start to get into trouble is with parabolas. That's a function, passes the vertical line test, but it is not one-to-one. It does not pass the horizontal line test. So it doesn't mean we won't find its inverse. What it means is we'll restrict the domain. We'll only look at a piece of that parabola, maybe this piece, and ignore the rest. And then it's one-to-one, and then we can find its inverse. So keep in mind, and this is a pretty important rule, that only one-to-one functions have inverses. Okay, now we're going to continue practicing finding these algebraically, and I'll show you how to check by graphing. So first, we'll find the inverse of f of x equals negative 2x plus 5. So again, more practice, and you can certainly pause and try it and fast forward to check if you'd like. So we'll call this y equals negative 2x plus 5. We'll switch x and y and solve for y. And because we're going to graph, I will write this in a better form. I'll separate that numerator and call this negative 1/2 x so I can see the slope, plus 5/2, and I can see the y-intercept. So the inverse of this graph, the inverse of f of x, is negative 1/2 x plus 5/2. Now keep in mind, our critical step in finding an inverse is switching x and y. So when I graph, what should happen is all my x and y values of my coordinates should be switched. So if I start with f of x equals negative 2x plus 5, I can graph that y-intercept of 5, slope of negative 2, and this is a sketch. It's certainly not going to be perfect, but it'll give you the idea. You can do it on graph paper. You can also look at this on your graphing calculator, which is well worth it. So there's my f of x graph. My inverse of f is negative 1/2 x, slope of negative 1/2, plus 5/2. So my y-intercept is 2.5. You're about there. And my slope is negative 1/2. So down 1 whole over 2. Right about there. Down a whole over 2. Or up a whole unit over 2 units. And that's a sketch of my inverse of f of x. Now, the key thing is if you did put these in your calculator and you looked at a table of values, all of the x and y values would be switched. So for example, in f of x, when x is, let's say, 0, to make the math easier, y is 5. Well, in the inverse of f of x, when x is 5, y will be 0. Oops. So you want to look at those tables of values. We could do another one. In f of x, if x is 1, we'll have negative 2 plus 5, y will be 3. So on its inverse, when x is 3, the inverse will be 1. And there looks like a 3, 1. My inverse 5, 0. Over here, my x-intercept. So it looks good. And you can certainly check those on your graphing calculator. The other quick visual is that inverses are the reflections of each other over the y equals x line. And so if I were to fold f of x along y equals x, I would land on the inverse of f of x. And so if you were told to graph an inverse right away, you would plot it and then reflect those good points over y equals x, or just switch the x and y of those good points. Alright, so let's try this one. Here I have f of x equals x minus 2l squared minus 7. Now right away you should be thinking, uh-oh, this is a parabola who's been shifted right 2 units and down 7 units. So it's not going to have an inverse the way it is. So we'll talk about restricting that domain in a minute, and we'll restrict it from its vertex essentially. But let's practice the algebra of finding an inverse first. So this is y equals x minus 2l squared minus 7. Switch your x and y and solve for y. So we'll add 7. We will undo squaring by square rooting. And we'll get y all alone. So the inverse of f of x is the square root of x plus 7 plus 2. Well, again, when you think about your graphs and your parents and the transformations on them, this is my parent square root that's gone left 7 and up 2 units. So if we start actually with the inverse graph, we go left 7, up 2 units, and I have my parent square root of x. Then I think about how it was a reflection over y equals x of some graph that's its inverse. Then you know how to restrict the domain of x minus 2l squared minus 7. This was a parabola, again, that's gone right 2 units and down 7 units. So if I take this right 2 units and down 7, there's the vertex. Now, I cannot graph the entire graph because it won't be one-to-one. If I graph this side of it, this is not the reflection over y equals x. So I'm only going to look at this piece of my f of x graph. So this domain, then, is all real x's that are greater than or equal to 2, the x value of the vertex or turning point. So we only graph the piece of the parabola that will allow me to have an inverse, that will make that function one-to-one. That is it for tonight.